Hey, I'm Dr. Ron England, and this is EGN3443, Probability and Statistics for Engineers. And now we're getting into a little bit of meat. This is, I think, Module 2. Yes, we're getting into some descriptive statistics. Yeah. Let's talk about what we're going to talk about. Well, there's a lot of stuff we're going to cover in the course, but right now we're going to look at, for this module, we're going to look at some basic measures. Central tendency and dispersion. Okay, you're going to. Well, I'll tell you what those are. But the other thing about this module is we're going to talk about data visualization. Now, for what we're doing in these simple statistical examples for this module, there's really only 3 plots we need to talk about: stem and leaf, box, and histograms. And then a little bit of the application of what we're going to do with this. So let's first get started with central tendency. Okay. When you ask about something, and it might be something that's statistical, you typically say, well, what's the average? Well, average is a measure of central tendency. But the reason we don't say just average is because there's more than one way to measure central tendencies. So we kind of want to know where that data centers. So if you said, hey, you just had the exam, and I say that the average was 82, and typically what you're going to do is you're going to compare what you made against the average, and that's how you're going to look at this. But the reality is it's a little bit more complex when you're dealing with a lot of different types of statistics. So when we say average, we're really talking about the mean. The mean. It's a simple equation. You've probably done this before. I don't really need to go over it. Sum of all the values, divide by n. That's kind of it. That's it. Now, there is a limitation. You got to understand a little bit more about the mean. We're also talking about 2 different things many times when we talk about the mean and the average. We're talking about the mean of a sample and the mean of the population, which, by the way, are not the same thing. They're not defined as the same thing. They may have the same value if you picked a really good sample, but they're not the same thing. One of the big things to know about the mean is that it has some limitations. The biggest limitation being outliers. If you've got one value that's way out from the rest of all the other values, it can skew that data in that direction and not give you a true representation of where the center of that data is. I don't really need to go over any mean calculation examples. You need to figure it out. There it is right there, but I'm pretty sure most of you can figure out how to solve for the mean of a sample. Now, next one is the median. So remember mean, you're going to use mean all the time. It's the mean. If you want to really understand the data, you got to be mean to it. Just remember that. That's the average. The normal one the one that you do. The next one being the median. Now in this case, you just take all the data and you sort it. And then you chop it right in the middle, and that's your median. That's it. Okay? Now, sometimes when you chop it right in the middle, it doesn't actually end up on one point. Not a problem. Okay? Because it depends on whether you got an odd number of values and an even number of values, whether you can actually find the number that's sitting right in the middle. Well, if that doesn't happen, it's simple. You just take the 2 values now that make up the middle and you average them. So the median may contain the mean. Oh, there's a sample for you too. So the last one being of the 3 measures of central tendency is the mode. And the mode is the value that occurs most often. Now, realizing when you talk about the number that occurs most often, or the value that occurs most often, guess what? You can have more than 1. You can have more than 2. You can have more than 3. So it can potentially be a little bit more challenging to say what's the true mode. Well, if it does occur more than once, if it occurs twice, you have a bimodal distribution. There you go. Okay. Now, so these are the 3 primary measures of what we call central tendency. That's just a technical term for trying to figure out where is the middle of the data? What represents, what single value is representative of the data? Now, knowing that if you've got data, one value is not necessarily always representative, but you do often want to be able to represent something with that single value. The next piece of this is the measure of dispersion. So, you collect some data and you figure out kind of where the center is, but sometimes it spreads out really wide, you got points all over the place, and sometimes it's nice and tight and narrow. Okay, well guess what? That is a measure of dispersion. Okay, you're quantifying the variability, how much variability exists in the data. Okay, and if I said that I took a sample of people's heights and it had a low variability, it would mean that they're all pretty close to the same height. Now, a good example of this is if you, let's see, well, a good example of this might be taking the heights of the members of a basketball team. They're all going to be tall, but they're all probably going to be pretty close to each other. They're going to have a variability that's going to be lower than if you did the entire general population, including every single age. So yeah. Now, it has a significance because the broader that is, and the real reality is if there is a high level of variability, especially in engineering systems, there's a greater level of challenge in actually dealing with how you do this. Another one being range. Range is simple. It's minimum, the maximum. The range is the difference between the minimum and the maximum. And typically the range is given as the difference between the two, but sometimes you'll hear it referred to as the minimum and the maximum as the range. You would have to actually calculate from that. So, for example, and the range it can tell you a lot of information. So, let's say, for example, and it's very also understandable by many people. So, if I said in Florida, the mean temperature on an August day, in the middle of the day, is 92 degrees. Then I said the range was 60 degrees. Well, if I said just 60 degrees, you'd be like, well, that seems like an awful lot. But let's just say the highest value is 100, which means if it's 60, the lowest value would be 40. So if I said the range on a summer day was 40 to 100 in August, the 100 might make a lot of sense, the 90-something might make a lot of sense, but then you'd be like, wow, 40 in August? But that tells you something. Now, I don't think the range of values and you can look it up. You guys are in my class. I fully expect for you to be able to use either AI or Google to find these values, okay? And actually not just find these values for August, but find them for every year. You should be able to do this. Okay, but understand what this actually tells you and how your ability to visualize the data from what you're given is important. Because I know that when I said the range was 60 degrees, now I'm talking in Fahrenheit, I often think in centigrade, so you just got to get used to that. But when I said the 60, it didn't mean so much. But when I said the range is the two minimum and maximum values, it probably meant a whole lot to you. Now, understanding the variance. There's one critical factor in your doing population variances. Okay? Note. Okay? Sigma squared, which is the population variance. S squared is typically given as the sample variance. When you're doing the population variance, you're looking at you're summing all of the entire population, x minus the mean over n. And when you're doing the sample, it's n minus 1. That is a key factor. And if you think about that, because the thing you're dividing by is reduced by 1, the variance is higher. Okay? But as n approaches infinity, they're both going to approach the same value of population and sample, which should also make perfect sense. Now, how do you do this? It's simple. It's the equation. I'm pretty sure I don't even need to cover the calculation of the variance. You do need to know the mean. You need to know the squares of the standard deviation, the square deviations from the mean of each of the sampled things, and you sum them all up and you divide by n minus 1. Not a problem. Now, standard deviation is what we typically use rather than variance. Okay, it isn't that much different. It's simply the square root. Now, the reason this is important is because it's actually in the same units as the mean. Okay, so why do we use standard deviation? If you look over at variance, which does tell you essentially the same thing because it's just simply the square of the value, but when you go back and you actually do the standard deviation and it's in the same units, it makes a big, it's more intelligible to you when somebody says the standard deviation, because you can think, oh yeah, it's in the same unit. So if I said you had a temperature of 100 with a standard deviation of 10, well, I'm talking about the standard deviation of 10 in those units, which would be degrees, okay, because it's temperature. All right, that's it for the calculations for this module. It's not all none of these are difficult, but I do want you to understand why we do use these things. Now, visualization. Well, let's start with the one, actually this one's pretty easy. This is, you've probably done this. We do, I mean, I know that the elementary schools do this typically on paper, the good old stem and leaf plot. Yay, yay, yay. Okay, so you got some numbers, you pull the first number over to the left, then the leaf is all the other digits that go with the piece afterwards. So if you were to look at, if you look at the examples I've got here, I think it's pretty explanatory. By the way, the third plot up here is what I would call a bimodal distribution, because you can see that it can around the number 7 and around the number 13, which is actually around the number 70s, the 70s, and then the 130s. You got little peaks there. That's actually kind of the purpose of doing the stem and leaf plot, because what it does show you is a little bit of how that distribution is put together. It gives you that information simply by looking at it. And that's what you want in the visualization. Nothing is better in statistical analysis than your brain and your intuition of how the data is actually looks. And the best way to figure out how that data looks is to come up with visualization to do that. Now, I'm going to give you some information about this a little bit later on about how you're going to do this. So the next one that we're going to talk about here is the good old box plot. Now, the box plot shows you is the median quartiles. Well, what does that mean? Well, the quartiles, if you take the data and you put it into 4 different ranges, first, second, third, and fourth quartile, with the middle being between the second and third quartiles, it shows you the middle piece there. Okay, now it does give you how you can look at skewness, and I think what I'll be able to best show you, and it also gives you a really good ability to spot outliers. So, for example, if you look at these like simplistic box plots that you got right here, you can see that, like in this case, the third one on the left one, the third one, because it's really broad, means that there's a higher level of, and you should be able to say variance, standard deviation, variability, all those are correct. Now, and then the other image that I'm showing you shows you the first and third quartiles in there, and the maximum and minimum values are also shown in this. You can see it. Okay, nice. Now, making these, you're using Python in this class. Just get used to it. Now, I don't say, if you need to create a box plot, a histogram, or we're going to talk histograms in a second. Here's what I recommend. take your data, go over to whatever your favorite AI is, they're all going to do this, and say, please generate me some Python code to visualize this, and you can tell it to do the specific plots, box, histogram, whichever ones you want to do. But if you don't tell it which one, you just say use standard statistical visualizations. I've tested this many times. It's going to give you the Python code for pretty much all of them. Now, the code that I gave you right here, one of the things that you can do very easily with NumPy is generate some random normal distribution. So if you don't have any data, it's not that hard to create some data. Most of the time, well, all the time in my example process, I take that back. I've got some assignments where you've got to use and generate some random data. So that one line of code does that. Not hard to do. Now, last one, histograms. The good old histogram. Histogram is probably the one that you're going to use. I mean, you've used histograms, but there's decisions to be made in the histogram. You actually decide some things. Like a histogram basically says how often does something in a specific range occur. Something between 10 and 20, 20 and 30, 30 and 40, 40 and 50. Okay, wait. 10 and 20. Somebody has to decide that histogram is going to go between 10 and 20. Okay, now you could also say, well, I really want to have a histogram with X number of bars, X being how many bars I want to have. Okay, well, you can say generate a histogram with dividing it into 10 equal, basically we call them bins, and how many values are in each of those. The one problem with that is that it sometimes, since it's going with 10 equal bins, you might have a bin that runs from 10.7 to 11.9, which is, I mean, it might give you a decent visualization, but you typically kind of want to go on to numbers that make sense. You need to be able to know how to do both. It's not hard. And the reality is I expect you to be able to generate the code, whether you do it yourself. I oftentimes do it myself, just simply because I'm using Colab. It autofills anyway. By the time I type in the first line of code, it's already figured out what I want to do, and it gives me the rest of it. I look it over, and I just accept it. Okay. If you're using Colab, if you're using most of the modern editors for Python, they're going to do that. Or another trick, if you write a comment saying what it is that you want to do, it'll generate most of the code for you anyway. But this class, I do fully expect you to use AI to generate code. I just expect you to know what the code that you generate does. So you generate the code, you look at it, and you save yourself a ton of typing. That's really all that you've done. Because if you look back at the code that I gave you there, like this code right here, plt.boxplot data. Okay, you feed the data, you make a box plot, you make a plot with the box plot, and then you show it. I mean, it's really, really not that hard to do. Okay, but you might not remember that the thing that makes the box plot is the box plot method. Okay, well, AI will. Okay, and sometimes the AI gives you code that doesn't run, I fully expect you to be able to debug it if that's the case. Alrighty, there's your visualization. Now, some visualizations are good for some things, and some visualizations are good for other things. Okay, so one thing is if you got 1 million pieces of data, stem and leaf plot is probably not going to work real well for you. Just anybody who's ever tried to do it, if you fed it, and the thing is you're not going to sit there and by hand and do a stem and leaf plot with 1 million pieces of data, but you would potentially ask the computer to create one, and then you're going to look at it and go, oh crap, I didn't mean to do that. Just understand that's a limitation. Box plots. Okay, well, box plots are really good for simple, straightforward visualization, especially if you're really interested in the variance of multiple data sets, comparing this experiment versus that experiment, because you're looking at those two boxes side by side, and it's pretty obvious if one of the boxes is big and the other boxes is small. Histogram, I really feel that when you need to understand the shape of a data set, how it actually looks shape-wise. The histogram does the trick. Now, be wary, because if you make a mistake in bin selection, you make them too tight, you make them too large or whatever, it may not give that to you. Realizing that if you make a whole lot of really small bins, it's a lot of work, but if you're using a computer, it's no work at all. And if you use really big bins, you lose a whole lot of it. I always think of it like a contour map. If the contours are far apart, you can miss mountains. Okay, if the contours are close together, it's a really freaking tight plot and hard to read. That's how I look at it, but I also do a lot of navigation. Alrighty. Now, where is this used? Everywhere. I mean, you can look at pretty much any application in engineering and you're going to use these statistics. Now, here's the big thing. What do you use? Now, the most used statistical software, and I didn't put an axis on, I actually had an axis on this plot, but you know what? It doesn't matter. Okay, Excel is the thing that is the most commonly used for statistics. You're free to use it. I don't have any problems with you using it at all, especially to manipulate the data. It's a good thing to do. In fact, a lot of times what I do is I manipulate the data in Excel, knowing that you can use Excel. Well, actually, I use Google Sheets more than I use Excel, because I can pull data from a Google Sheet with Colab very easily if the Google Sheet is in Drive, because Colab is integrated with Drive. But it really doesn't matter, because you can use Pandas. Pandas is a library in Python to pull the data from Excel. So the Excel is a good tool for manipulating and playing with the data directly. I don't use it so much for the statistical analysis of the data. Why? Because it can do all the statistics I just did in this lecture. No problemo whatsoever. But as we get into the more complex statistical analysis, Excel doesn't have them. You would have to actually code them yourselves. Well, Python does have them. So if you look at the next two in this, Python and R, you'll notice that, and I can tell you right now, for scientific and engineering statistical analysis, it's Python and R. But I can say Python and R almost interchangeably, because there's nothing you can't do. There's nothing that you need R for that you can't do in Python, because Python will integrate the entire R library if you need it. And I can tell you, there's very few statistical analyses that you actually have to have R, that's in R and is not in Python. My dissertation had a whole bunch, but we are also creating an entire field of statistics to try to do the stuff that we were doing in my dissertation. So that was a totally different approach. And then after that, we actually created another field of statistics, another whole branch and methodologies and statistics that didn't exist before, to do some of the stuff that I did in my postdoctoral work. Okay, we were coming up with better ways of predicting things. And actually, now it's become very applicable, because I can tell you what I was predicting was extreme weather events. And I was trying to prove whether extreme weather events were becoming more and more common. By now, I don't even need to give you the answer to that question. Yeah. So, there you go. But you know what? Until you prove it statistically, it doesn't actually. It's just anecdotal evidence. That's all it is. Now, what are your key takeaways? Well, you need to know this stuff. You need to know. I gave you some other resources here, but if what is covered in this lecture is the stuff you just have to know off the top of your head. As we get into the other lectures, as we get further and further into depth of this, not so much. But this stuff, this has to be there when you need it on your brain. Okay, we're going to move on to modules as we start going into much more complex distributions, and we start talking about discrete versus continuous data and how you're going to analyze those later on. Well, all this stuff still applies. But now we'll be moving into more complex things. I'm hoping that you enjoyed this. This is a long lecture for me, 25 minutes. I'm looking at the clock here, but I'm trying to make this stuff as interesting as possible because I know how dry statistics can be. But when you're actually doing statistical analysis, it can also be fascinating. So I hope you catch some of my love for statistics.